pull it out and you stick in a sulfur atom, and now you put a potential across there, you're going to be able to conduct electricity. Current is going to flow across that. And the reason for that, the explanation, is that phosphorus material has a certain number, or the phosphorus atom has a certain number of valence electrons, right? How many valence electrons does phosphorus have, guys? Five valence electrons, right? So when we're building phosphorus, we're in that third row, so we're filling up that third subshell. We've got two subshells beneath us that are filled. The first subshell and the second subshell both all have their electrons, and now it's that third subshell that's being filled, and phosphorus has 5 electrons in it. So the solid phosphorus material tends to want to feel like all of these atoms that are donating electrons are donating 5. When you dope it with a material that adds an extra valence electron, how many valence electrons does sulfur have? 6. So when that happens, you essentially create these extra electrons that are higher in energy, and they're more loosely bound to the material because they're higher in energy. And when electrons are loosely bound, they're easily subjected to forces. They respond to forces. So by adding a dopant to this material that has extra electrons, you've supplied to that material high energy, loosely bound electrons that will respond when an electric potential is placed across the material. This is called N-type doping. Because we've added a material that's negative with respect to what we had before. It's got more electrons than the bulk matter. Go ahead.
Why would direction matter? In a diode, the electricity can only travel in one direction. So if you put the sulfur in, why is it that it only transits in one direction?
I don't know. We'll talk about diodes in just a second, though. We're getting there.
Okay.
And then you can ask me the question, and I'll be able to explain to you again that I don't know. Okay, so this is our N-type doping. And with the N-type doping, another way that they draw this is you imagine that the material has kind of an abundance of negative charge. So every place we put those sulfurs, we're just going to imagine there's an extra negative charge hanging out. There's another way that you can dope this material that will get it to conduct electricity. So let's draw the same material again. A bunch of phosphoruses. Now, we're going to dope this with silicon. Yeah? Silicon has how many valence electrons?
4.
Huh?
4.
4. It says 1 fewer valence electrons than does the phosphorus. Right? So, again, the bulk material, the bulk phosphorus material, has these orbitals available to the electrons. They like to have each of the atoms in the material donating 5 electrons. But these dopants here create vacancies. All of a sudden, there's an atom that would like to have more electrons than it has. Right? The bulk material wants to feel like every single atom is donating 5 valence electrons, but these silicon dopants are only donating 4 valence electrons. What that creates is it creates low energy orbitals available for electrons. These little holes, as they're referred to, represent available energy orbitals that electrons can enter into. Low energy available orbitals You take a potential and you stick it across this positively type or doped material, and you're going to get electron flow. You can almost visualize it as electrons bouncing from one positive center to the other. That's not exactly how it works. Once you get into the realm of quantum mechanics, nothing is as it seems. But suffice to say that you've created space in this material for electrons to move across. You've created orbitals that electrons can travel. So 2 different ways you can get this material to conduct. You can have a N-type dopant, which adds extra electrons that are inherently more loosely bound and respond to potentials. Or you can do a P-type dopant, where you create space available around the atoms for electrons to migrate into. Now, here's where how a diode works. You draw these 2 materials, but instead of labeling them, I'm just going to note their actual charges on the dopant species. So, silicon dopant, we're going to indicate it by a positive charge because there's fewer electrons there than the material kind of wants to have. If we sandwich these 2 materials together, we take a P-type dopant, a positive type dopant, and an N-type dopant, and we bring them together so that they're physically in contact. What happens is that in this region right here, the positive charge and the negative charge kind of act to cancel each other out. And so this region in here ends up right at the point of contact being relatively neutral. Now, this top end where the N-type dopant is still kind of negative, and this guy down here where the P-type dopant is still kind of positive. And so by sandwiching those 2 materials together, you've created what looks like a capacitor. Right? What's a capacitor look like? You've got a plate that has an excess of negative charge on one plate, and it's got a deficiency of negative charge or an excess of positive charge on the other plate. Well, that region of the P-type dopant is starting to look like the positive plate of a capacitor. The region of the N-type dopant is starting to look like the negative region of a capacitor. And I don't know if you guys know about this, but well, you do know about this. If you take an electron and you allow that electron to start off at the negative side here, and you allow it to flow to the positive side there, it's going down in electrical potential energy, correct? Right? It's negative charge moving closer to positive charge. It's negative charge moving away from negative charge. And so it's being attracted by the attractive forces. It's being repelled by the repulsive forces. It's moving down in electrical potential energy. Well, guess what happens when you drive a current that direction across your diode? Energy is emitted as light. Right? You create a situation where you've got a higher electrical potential and a lower electrical potential, and you drive the electrons across that potential, and they'll do what charge does when it moves across potentials. You know, if it's going from high potential to low potential, you're emitting energy. If it goes from low potential to high potential, you're absorbing energy. In lab, you're going to have a bunch of diodes. Now, the diodes end up looking like discrete emission because this energy gap between here and here is fairly rigidly defined. So there will be very specific frequencies of light that are emitted for a specific diode arrangement. In lab, we'll have red diodes, blue diodes, green diodes, yellow diodes. You're going to be able to take your spectroscope and point the scope directly at the material, and you'll get a readout of what that emission spectrum is. And so that's what you're doing in lab this week. We're gonna look at continuous emission, discrete emission. For continuous emission, we've got black body radiators that are simply emitting radiation because electrons are getting jostled around. For discrete, we've got the hydrogen atom and the diodes, and that's it.